Alright, so last time we said those solar collector, whether without any cover or with cover, they usually follow that curve. That curve is the efficiency of the collector, which is, it's defined as what? Q useful over Q input. Right? Q useful is the m dot water CB delta T water, how much Q you actually absorbing from that solar collector. And the Q input would be the incident radiation, I, whatever watt per meter square, time the meter square. Okay, that's the incident power. So now this efficiency is useful to figure out how much heating you will be able to absorb or get into the application, whether it's like a swimming pool or a house or a dishwasher or whatever the heating place you are heating. You will be, through this equation, through this curve, you'll be able to calculate the m dot output, or useful, by multiplying the efficiency times the input radiation, times the area. Alright? And we finish by saying that the curve will get higher if you start adding more and more glass covers, right? And especially if the collector is out of selective material that absorb and does not radiate. So then the curve will become really that high. And the last thing that we talked about was this point. We finished this point by saying this is the point of maximum temperature. Okay? And we said that at that point you cannot get any hotter than this. And that point the efficiency is 0, meaning all the radiation falling is dissipated by heat. That's why you cannot get any hotter than this. Okay, and we said that would be similar to a car in the summer with the window closed. It will get high enough, and after that the temperature does not get any higher than this. Why? Because at that point the seats and the driving wheel and everything inside is radiating enough to dissipate all the input, and that's why they reach steady state. All the input equal all the losses, right? And that scenario, basically the knob on the pipe will be closed, so you can get the water to be that hot in the collector if you shut down the pipe. So if you shut the exit and the inlet and you just let the water get trapped inside, it will get as hot as this point. Okay, notice the x-axis is what? T average minus T ambient over I. So T average, that's the temperature inside. T ambient, that's the air that we are leaking to, dissipating heat to, and I is the incident radiation. Okay, very good. So that equation is basically written like this, and our job is to sometimes this equation is given straightforward to us, and sometimes you really have to extract the number from the graph or from the table that will give it to you. All right. So that efficiency is a, as you see, it's a linear. So a linear equation would be, any linear equation can be expressed as, here is x, here is y. It will be mx plus b. There is a slope and there is intercept. The intercept would be the part that you hit the y-axis at, and the m is the slope, right? The slope of the curve. So this is how they actually get those numbers for the measurements. After they do the measurements and they plot, they will be able to get the slope and the intercept. So eta is the y-axis, the t minus t over I, the incident radiation, the watt per meter square. This is the x-axis, the x variable. So therefore this is the intercept and this is the slope. So if you go to the chart and you read the intercept is like 0.7. What's that 0.7? It will be the FR tau alpha. Okay, let's remember what are those numbers. So the tau and the alpha, this is the transmissivity and this is the absorptivity of the collector. So alpha is how much he absorbed, tau is how much is the glass cover is allowing you to go through. Okay, and the FR, it was defined, I guess, earlier here. I guess the first time we saw it is here. So what is the FR? So note that over here the chart is written as T average minus T ambient over I. Again, T average is the average temperature inside. The average temperature inside is probably a good approximation for it is what? T inlet plus T outlet divided by 2. That would be the average inside. Okay, so now when I am buying that thing from Walmart or buying it from Lowe's or Home Depot, and they have this chart sticked basically as a sticker to the collector, and I'm trying to figure out, will I be able to get a good shower in the winter or not? How hot will it get for me? If I use this x-axis, T ambient, that's easy. I know what's T ambient in Tulsa, Oklahoma in different days of the year, right? I can just Google what's the average temperature in December, January, whatever, right? The inside radiation also exists, especially if you know the tilt angle. You're going to hang this on the top of the roof. You know that at 45 degree, the roof is tilted 45 degree, you'll be able to get this I. How much is watt per meter square on a tilted roof? But what's really hard to get is the T average. You will not be able to get the T average. And the reason why you cannot get T average is why it's super hard to calculate T average, and therefore it's hard to calculate the efficiency. Because T average is T inlet plus T outlet over 2. So I can know T inlet, it's probably, well, the temperature coming from my house. The water will come into my house and it will go through the collector. Or maybe we know the temperature of the ground. We can assume the temperature of the ground is a little bit lower than the temperature of the air. And we get that from table. But how can I get the T outlet? See, I don't really know the T outlet yet because I didn't figure out how much flow rate I'm gonna send through this guy. If I shut it down, T outlet is probably gonna be T max. And if I have high flow rate because we are using the shower and the dishwasher and the T outlet probably will be T inlet. If I use the maximum flow rate, right, I keep pumping water all the time, theoretically speaking, the T outlet will be the T inlet. Like the water will have no chance to get hot because it's just like all the water basically come and go like this. Best worst case scenario basically. So my point is, it's very hard to calculate T outlet, and therefore this is not really useful. So what's useful if they have done this with T inlet minus T ambient, then it's really useful. Okay. So in order to do this, in order to convert this equation that has T average minus T ambient to become T inlet minus T ambient, Tn minus T ambient, they have to do a correction factor, and that correction factor is the FR. So FR is a collector heat removal factor. Okay, and it's basically a way for you so that you can adjust the equation or write the equation in terms of things that are really good for design. T inlet minus T ambient. Okay. So now in this new coordinate system that has Tn minus T ambient over I, if you plot the eta against this x-axis and it follows a straight line, then you got yourself your intercept and you got yourself your slope. And so from the data you can get those numbers, and therefore you will have the efficiency equation. And then you can use this to check what will happen in different months, in different city, in different stuff. Okay, and so let's jump a little bit. So this would be the graph. Okay, so here's efficiency, and over here it's T inlet minus T ambient. T inlet, not T average. Okay, so now when someone come in this, of course data will be scattered, as we all know. Whenever you measure something, it's never exactly correct. There is always error. But if you plot the best fit line through it, and you extend that line over here, and you read 0.8, that 0.8 that you just read, because it's 80%, so it's 0.8. That 0.8 is what? That 0.8 is FR tau alpha. Okay, that is the intercept. Correct? And if you figure out the slope, what is the slope? It's basically the delta y over delta x. Okay, so you can basically tell yourself, well, the x-axis went from 0 all the way to we can do it over here, from 0 to 0.2, and during that time the y dropped from 80 to 60 or 0.2. So the slope will be delta y over delta x, and because the dropping thing, it's minus. The y dropped as x, so that's a negative slope. If it was increasing, you increase the x, the y increase, it will be plus slope. So you calculate the slope, and then what did you just calculate right now? You end up calculating the minus FRUL. So hopefully it will be minus, because there is minus FRUL, but you basically put your hand on FRUL. Okay, what's UL? The overall heat transfer coefficient of that box. Right? Point is, you got yourself the equation. Very good. So now, like you can imagine, they do those tests on in the lab, right? They can put the sun, not the sun, they put like light or stuff that is exactly 1 sun, 1 per meter square, and they keep calculating you can measure the water outlet. They can just measure the temperature, and therefore they will be able to calculate that efficiency. Okay, but when they put the sun normal to the plate. Now in real life, the sun is not gonna shine normally to the plate. The sun is gonna do what? It's gonna come with an angle, and hopefully, if you have the really good optimization, in the middle of the day, it will be the smallest incident angle ever. Remember the incident angle, we call it, what did we call it last time? Theta I. Remember the equation for theta I that hopefully you wrote at the back of your book? Everyone, right? Because it's not in our book. We wrote it in pencil at the back. Did we? Hopefully. You should write the theta I equation there. Right? So that theta I, if you did a great job in the middle of the day, it should be 0. Like the sun is really normal to that plate. Okay, and then the sun starts moving away, and the incident angle will increase. Worst case scenario, theta I is 90. If theta I is 90, that means the sun is parallel, not normal, parallel to the collector, and the radiation would be 0. Right? But even if the angle is not 90 but like 80 or 70, that's still horrible. Why it's horrible? If the sun is falling not normal to the plate but at 70 degrees to the plate. Why that's horrible? I mean, 2 reasons. First, you are going to get cosine 70, which is like pretty small number. Optimally, you want cosine 0. You get all the radiation. Cosine 70, that's not a good number. But on top of that, that angle will result in huge reflection. So the reflectivity of the solar collector would end up suffer. He will reflect a lot. Okay, and so that's why there is, so this is the equation, right? But then they tell you that equation, especially the tau alpha, that transmissivity and alpha, you did it with normal radiation. That n sub n is for normal radiation. You need to multiply it by another correction. That correction is the incident angle modifier. So after you calculate the theta I, the incident angle, there is an equation for K, the punishment. The punishment factor, that say if you come with like really big angle, not normal to the plate, you're gonna have very small transmissivity. You're not gonna get all that radiation going through. Alright? So there is ways to plot or to represent that incident angle modifier. Sometimes he will give it to you in an equation, just function of theta I. I mean, he call it here cosine I, but it's really theta I. That's what I'm trying to say here. Theta I is the I. Sometimes he give it to you like this, and sometimes he will just give it to you as a table. right? Not this table, but there will be a table where he give you the theta I as function of the incident angle. All right. So this is the example in our book, and he was basically saying use this chart to give me what? Give me the FR, give me the UL. He's asking you to read the intercept and the slope so that you can get the equation basically. Assuming that tau is 0.9 and alpha is 0.92. Okay? And then calculate the temperature when the flow rate is 0. When the flow rate is 0, that means he closed the pipe flow. So what is that point? Collector temperature when the flow rate is 0. What would be that point? Where is it? If we shut down the water in the collector, where would we be? Here or on the other side? The other side, huh? If we shut down the water in and out, water is trapped inside this collector receiving sun. That's your car in the summer with closed window. You have to prop the window so that it doesn't get that hot. So if you close the window, you will go all the way till here, where the efficiency becomes 0 and the temperature become max. Right? And so we will get this point once if we have the equation. If we have the equation, we'll be able to do this. Okay? So watch what he will do then. He will start trying to measure the intercept, and you say, then this is 0.8, and he's trying to calculate the slope. It's 0.4, 0.8 plus 0.4 just from the curve. Okay. So amazingly, when we in the homework, when I will give you actual collector data sheet. The company make the collector, they test them at third party in the company in another testing place in Florida or something, and they will give you the data sheet for the collector. And in that data sheet, they will tell you directly what is the intercept and the slope, and they will call it like this. The intercept is this much and the slope is this much. Okay, so you don't have to actually read it from a chart. You can actually, you will be given the number. Okay, so he calculate this and he calculate the slope, right? And he tell himself this must be FR tau alpha, and since I know tau and alpha, I can get the removal factor FR. Okay, and so he does this. Okay, 0.8 equal to this. I was given tau and alpha because I know the glass, I know the paint material, so I know it's alpha. Therefore, this is FR. The second part, he want to calculate the UL. Okay, where is the UL? It's on the slope, FR UL, and we just calculate FR from the intercept. So he say, well, the slope is minus 0.4. Okay, so this minus 0.97 UL, minus 0.97 UL, and you got the minus 0.97 from the previous part, is equal to the slope. And he look at the way he calculate the slope. He pick 2 points. So when you go from 0.5 to 0.8, 0.5 to 0.8, and he calculate the x-axis, going from 0 to 0.3, 0 to 0.3. That's the way he calculate the slope. Okay, and notice that the intercept, what unit does the intercept has? What unit should the intercept have? Efficiency. What's the efficiency of? What's the unit of efficiency? 0, dimensionless, right? So and that's perfect because FR and tau alpha, they are all factor. They are all ratios. They are all dimensionless. But the slope will be this guy over this guy. This guy have no dimension, but this guy got dimension. Why? Because the x-axis is T minus T over I. So that's degree Fahrenheit over, or degree Kelvin over, what's I? Watt per meter square. So the slope will have a units, and that's good because the overall heat transfer coefficient, does anyone remember from heat transfer what's the unit for the overall heat transfer coefficient? Remember the heat transfer equation? The most famous equation in the heat transfer book? Q is UA delta T, right? That's what the course was about. Heat transfer book was about Q equal UA delta T. So what is the unit of the U then? Must be watt per meter square Kelvin. So that UL is watt per meter square Kelvin. That slope should be in watt per meter square Kelvin. Okay? So when he calculate the slope, in English unit is the watt will be BTU per hour. Like joule per second, that's what the watt is. So BTU per hour, watt per meter square, feet square, degree Fahrenheit. Watt per meter square Kelvin. Okay? So he calculate the slope and he say to himself, and that slope is FRUL. Right? And therefore he can calculate the UL for himself. Okay? In our homework, probably will have it in watt per meter square Kelvin, and you'll be able to calculate the U in that units. Right? So the rate at which the collector can deliver useful energy when the irradiation, that's I, is this much BTU per feet square hour. The ambient temperature is this much, and the inlet water temperature is this much. So what is he doing? He's giving you the x-axis. He's giving you the temperature of the inlet water, the temperature of the air, the incident radiation, and he said, now what is the efficiency? So that's basically just go read or substitute in on the equation, right? And you get yourself the efficiency. So just get yourself the x-axis, right? And tell yourself that the useful will be the incident radiation times this efficiency. And so that's what he does. He calculate the x-axis and he will calculate the efficiency, become 0.65. Alright? And so he tell himself now this 0.65, if you multiply by the incident radiation times the area of the collector, you will be able to calculate P's. Okay, if this is not clear, what I'm saying is Q useful is the efficiency multiplied by I incident radiation times the area of the collector. Okay, now this area of the collector, actually you think it's straightforward, it's a little bit confusing. Why it's confusing? Because when we open the data sheet of any collector, you'll find they have two areas. They have the total area and they have the aperture area. Okay, the aperture area is the glass area. It's the area that the radiation goes through. The total area is, or they call it the gross area. The gross area is what? It's basically how much he will take on top of your roof. How much will occupy? What's the difference between the two of them? Why the aperture area is not the same as the gross area? Because the guy who designed the frame did a horrible job. And he had like a really big frame. Maybe it's not a horrible job. Maybe he wanted to be really good insulated, and he figured, I cannot make it insulated if you give me that thin wall. I need big wall. I need to put some kind of insulating material. Therefore, I need this. Alright? So now the question for you is, when I'm calculating that, I'm trying to calculate the Q useful, how much water is going to be heated. I need to calculate this. What area should I use? Should I use the aperture area or should I use the gross area? What area should I use? I open the data sheet and they have two areas. You would think, right? That's the confusing part. You would think I should use the aperture area because that's what the radiation is going through. Right? But no, you use the gross area. Use the total area. Why? Because that's how they define or measure the efficiency on. They measure, and it's actually, when you think about it, it's really fair. This is how much area you are occupying on my roof. That's what I should base the efficiency on. The fact now you decided to have a very small window, that's not my job as a user. I give you 2 feet square in my roof, you owe me this much area, basically. That's what we use for this is how much input radiation is falling on. It's not falling on your glass, it's falling on your design. Total area. Okay? Anyway, it's not about fairness, it's about how they define the efficiency too. So they define of the total area, we use the total area. Okay? So don't overthink it. That's basically what they define the efficiency on. Right? The point of maximum temperature, that is the point of maximum point of zero efficiency, and so you extend that line, or mathematically you just set efficiency equal to well, zero. If you set that equation equal to zero, the temperature here is Tmax. So right, so this equation, and by this equation you already got what yourself, you got the FR tau alpha FR UL, and you know how much incident radiation, you will be able to calculate Tm. Okay, so we can use this method to basically figure out a collector left in on the roof in Tulsa, Oklahoma, find out the maximum temperature it can reach in August, July, June, right? And you'll be able to basically get it just by varying the incident radiation during those months and the ambient air during those months. Tmax and incident radiation, you'll be able to calculate how hot it will get. Okay. Of course, it gets hotter and hotter if tau is bigger and if alpha is bigger, right? You can see that if you put this on the other side, you will see that the temperature is related to tau and alpha, right? So that's what they did. They set equal to zero. They figure out the temperature 191 degree Fahrenheit. Okay, that's how hot it will get. So this is a typical data sheet you will get for different collectors. Okay, so this one for I guess this is the supplier, this is the company, and this is the model AE-21E. Okay, I'm going to give you another one for the homework. Just look at different number. But what we need from this data sheet is, look at this, the gross area. The gross area, that is the area that we will use. Okay, net aperture area, good for you, but we are not going to use your 1.77 meters square. We're going to use the 1.9. So gross area and aperture area. Again, use the gross area. Okay, so what number we want? We want this, the intercept and the slope over here. Technical information. Okay, so the intercept is 0.66. What's the unit? Nothing. That's basically 66% efficiency. That collector maximum efficiency is 66%. Okay, and you get this maximum efficiency when what happened? When the water is completely running all the time through the collector, so the collector does not get that hot, and that's why he go to the maximum efficiency, because he does not dissipate that much. So then why is not 100%? Well, there is reflectivity, the plate does not absorb, right? But he doesn't lose that much. And the slope is watt per meter square degree C, minus 6.37. The slope has to always be negative, and the unit is, do I need to convert this to watt per meter square Kelvin? No, it doesn't matter when it comes to delta T. Degree Kelvin and degree C is the same, right? So we don't worry about this. And what about that incident modifier? Remember the incident angle modifier, the Kn, the K that was multiplied by the tau alpha, it's over here. He basically say the incident angle modifier is basically this. So he's saying that S is 1 over cosine theta minus 1. So you calculate the incident angle and you calculate the S out of it, and then he give you an equation for the K. So depending on the incident angle, you get the K. So if theta is 0, let's check this. Sanity check. If theta is 0, that's perfect, right? So it will end up being what? 1 over 1 minus 1. So S would be 0, and the K would be 1 plus 0.02 times 0 minus 0.086 times 0. The K would be, help, 1. The K would be 1. If incident radiation is basically theta is 0, that's the normal radiation. You don't get any punishment. It's only when theta start to get bigger and bigger and bigger, then that guy will kick in and that radiation will get punished by a correction factor. Okay? Now, what is with there is a second order equation and there is a linear equation. What is that? So you will see this a lot in industry actually. You will see that when they measure something and that something is doing this. I mean, it's clear to my eye that this is a second order. But no. Is that green curve is horrible? Not really. I mean, it's not the best fit, right? And it kind of like really undershoot in this area and overshoot in that area. But overall, it's not bad. So they rather use linear fit, even with a small margin of error, especially if the margin of error is not really a big deal. And so that's why they will tell you, well, here is the best fit, the second order, right? But you can see it's minus 0.08 S square, and S square is already small. So when you hit it with minus 0.08, we are talking about like 10% error. So they say, well, forget about the 8% error, let's just do linear fit. Okay, that's for the K. And also, so the equation, this equation, the intercept and the slope, that's a linear equation, right? This curve that we are trying to approximate is it really linear? No, it's not. It's really a little bit second order. And every year I used to give a student a free quiz if they can tell me why this curve shouldn't be linear. And no one has ever done this correctly. So hopefully this year we'll get someone that can explain to me why this curve should not be linear. Okay, so this curve should be a little bit second order. Okay, and so for a free quiz, if you can figure out why this curve should be actually second order, not linear. So when they give us the intercept and the slope, this is to make our life easier. But if you really want to do a great job, here is a second order equation. But you can tell that this is, what is that? Minus 0.0019. So 2 zeros, and then not even 7 next to it, or so, like no 2. There is 19 next to it, and it's multiplied by the P over I, the P square over I. What's P squared? Ti minus T ambient. So he's saying it should be a second order of the temperature, right? So if you want to do a great job, you do this, but if not, you will just basically use that intercept and that slope. Okay, and you can see, so the accurate equation is 0.69, the approximate equation is 0.70. So you know what's 1% between friends, you know, 0.69, 0.70. So that's why they rather have the linear fit. And in one homework problem last year, I basically told them, okay, I want you to calculate using the linear fit, and I want you to calculate using the second order, and compare the results. And not surprisingly, the results from both scenario are almost the same. So, you know, why would we worry about the second order if it's really splitting here basically, right? But you get free quiz for splitting the hair right. If you can figure out why it should be second order, you get yourself second order. You get yourself a free quiz, and the glory that go to your recommendation letter, because I would say that student solved a puzzle that stayed for 10 years. No one ever solved that before him. Okay, very good. So we if we are given this chart or this table, we can immediately find out the intercept and the slope, and therefore we got ourselves this equation, and we can do all kind of things. We can find the maximum temperature. We can find for any temperature basically what is the efficiency and therefore how much Q useful, right? And we can vary it for different I, different radiation from different months, and we can vary it for temperature, different T ambient during the months in Oklahoma, right? Questions? So put your answer on a postcard and send it to me. No, write it down and email it to me. Then I'll tell you whether you had a free quiz or not. Okay. All right. So this is the equation. If you didn't write this at the back of your book, this is the theta I equation. This needs to go in the cover of your book, because with that theta I you can calculate the K, the incident angle modifier. And let's take a 15 minutes break and we'll start again at 7.